Hi everyone, in this video I am going to discuss about Linear Variable Differential Transformer LVDT. It is the most important topic for the students of EEE as well as those who are preparing for competitive exam. If you find this video helpful, please like, share and subscribe to my channel for more education content. Let's get started. The LVDT is the most widely used inductive transducer to translate the linear motion into electrical signals is the Linear Variable Differential Transformer. LVDT is a differential transformer consisting of a single primary winding P and two secondary winding S1 and S2 wound around a non-magnetic and insulating material. The secondary windings S1 and S2 have equal number of turns and are identically placed on either side of the primary winding. A movable soft iron core is placed inside the former. The displacement to be measured is applied to the arm attached to the soft iron core. In order to overcome the problem of eddy current losses in the core, nickel iron alloy is used as a core material and is slotted longitudinally. Working of LVDT. The primary winding is connected to a AC source of voltage varying from 5 to 25 volt and a frequency ranging from 50 Hz to 20 kHz. Since the primary winding is excited by alternating current source, it produces the alternating magnetic field, which in turn induces alternating voltages. The output voltage of secondary winding S1 is ES1 and that of secondary winding S2 is ES2. In order to convert the output voltage from S1 and S2 into a single voltage signal, the two secondaries S1 and S2 are connected in series opposition. Therefore, the output voltage of the transducer is the difference of the two voltages. Differential output voltage E0 is equal to ES1 minus ES2. When the core is at normal position, null position, the flux linking with the both secondary windings are equal and hence equal EMFs are induced in them. Thus at null position, ES1 is equal to ES2. Since the output voltage of the transducer is the difference of the two voltages, the output voltage E0 is 0 at null position. Now second case. Now if the core is moved to left of the null position, more flux links with secondary S1 and less with winding S2. Hence the output voltage ES1 of the secondary winding S1 is more than ES2, the output voltage of the secondary winding S2. The magnitude of the output voltage is E0 is equal to ES1 minus ES2 and the output voltage is in phase with secondary voltage. Now case 3. Similarly, if the core is moved to right of the null position, the flux linking with secondary winding S2 becomes larger than that of the winding S1. Hence, the output voltage of ES2 of the secondary winding is more than ES1 of the output voltage of secondary winding S1. The magnitude of the output voltage is E0 is equal to ES2 minus ES1 and is 180 degree out of phase with the primary voltage. Thus, the linear variable differential transformer output voltage is a function of core position. The amount of voltage change in their secondary winding is proportional to the amount of movement of the core. Hence, we have an indication of amount of linear motion. By nothing which output voltage is increasing or decreasing, we can determine the direction of motion. Any physical displacement of the core causes the voltage of one secondary winding to increase while simultaneously reducing the voltage in the other secondary winding. The amount of output voltage may be used to determine the displacement. The variation of the output voltage against displacement for various positions of the core. The curve is practically a linear to small displacements. Beyond this range, the curve starts to deviate. In practice, output voltage is not 0 at null position but have some residual voltage at null position. But it is usually less than 1% of maximum value of the output voltage in linear range. The residual voltage may be either due to the magnetic unbalance or due to electrical unbalance. Presence of harmonics in input supply voltage produces in the output voltage because of saturation of iron core. It also contributes to residual voltage. Stray magnetic field may also cause for residual voltage, which may be overcome by using magnetic shield slotted longitudinally. The advantage of linear variable differential transformers are The output of LVDT is practically linear for displacement up to 5 mm. The displacement has a very high range of measurement of displacement. The LVDT has infinite resolution as it gives stepless output, and it has no mechanical element to change output in discrete steps. Nowadays, transducers are available with resolution up to 1 micron. LVDT has high resistivity. It usually varies from 10 mm to 40 mm. The LVDT gives a high voltage, and many times there is no need for amplification. LVDT can be used for high frequencies up to 20 kHz. Absence of sliding contact makes LVDT a more reliable device. The LVDT has a very low hysteresis, hence repeatability is excellent under all conditions. It is rugged in construction, so it can tolerate shocks and vibration without any effect. It is simple in construction, and by virtue of it being small and light in weight, it is very stable and easy to align and maintain. Most LVDT consume less than 1 watt of power. Disadvantage of LVDT: the larger displacements are required for differential output. They are sensitive to stray magnetic fields. Sometimes the transducer performance is affected by vibrations. The receiving instrument must be selected to operate on AC signals, or to demodular network must be used if a DC output is required. The dynamic response is limited mechanically by the mass of the core and electrically by the frequency of applied voltage. The frequency of the carrier should be at least 10 times the highest frequency component to be measured. Temperature affects the performance of transducer. These are disadvantages of LVDT. Application of LVDT: it can be used to measure the displacement, force, weight, pressure, and position. Now I am going to tell about rotatory variable differential transformer, RVDT. It is a very convenient device for measuring angular displacement and operates on the same principle as LVDT. Where the output voltage varies linearly with the angular position of the core, it is similar to that of LVDT, except that its core can be shaped and be rotated between the windings by means of a shaft. The operation of RVDT is similar to that of LVDT. At null position of the core, the output voltage of secondary winding S1 and S2 are equal and in opposition. Therefore, the net output is 0. Hence, angular displacement from the null position will result in a differential voltage output. The greater this angular displacement, the greater will be the differential output. Thank you.